So this project is worth 50 points. And what I like about it is, yes, you have to use science, but you also can be creative. And I like that because everybody is going to design a stick, and also you're going to design an experiment to use your stick with. They got that? So what I'm going to do is try to spell it out exactly what I'm looking for. And he said, I got it. I got the rules. I understand how the rules work. And then it's a matter of you spreading your time out a little bit. For example, I'm not expecting you to go home tonight and make this stick. But sometime, I would say, in the next week, you probably want to make the stick. You get that? So you say, well, it gives me a week. I can do that. And then while you're making a stick, you could also be thinking about, what are you going to do with the stick? What experiment are you going to do? And then you have to decide, hey, I need to get at least 20 people to do my experiment. So then you got to have time to test people. You get that? So it may only take about a minute to test a person, but maybe you have to get 20 people. So let me go ahead and spell this out for you. What's going on? There was an equation last chapter, and we used it with the dollar bill. Do you remember that? We're talking about why is it that people think they can catch the dollar bill, but they can't quite catch it? Because it only takes about 1/7 of a second for half a dollar bill to get through your fingers, right? But the fastest reaction time between your eyes seeing the dollar bill dropped and by the time your fingers can do that is about 1/8 of a second. So you actually miss it by just a 1/7 of a second, sorry. You only, 1/8 of a second. You only miss it by a little bit. So what I want to do is, I thought about this. So we've been doing this project for 20 years, but so what you're going to do is it's called a reactometer. And what you're going to do is you're going to make an object that can actually measure somebody's reaction time. Okay? This is just one way of doing it. By the way, it's worth 50 points, but I have gotten up to 60. You can get up to 60 points if you do a really good job on your stick or you do a good job on your experiment. You can get extra points, okay? All right, so here's our equation. Does this equation look familiar to you? Oh, I guess not, because I didn't turn that on yet. Okay. All right, sorry. All right, we'll take a look at the equation here, and I'll get it on the screen here in a minute. This stick's going to fall, isn't it? It's going to be in free fall. And what you want to do is, in this case, we're going to find time. Distance is going to be put into the equation to solve for time. Most of the time, you put time in there and solve for distance. But what we're going to do is we want to solve for time. So let me show you how this works as soon as it comes up. Okay, there we go. Now, everybody ready? Now watch. If you multiply both sides by 2, it'll get rid of this half, won't it? Then it goes 2d equals gt squared. Then divide both sides by g. Okay, this is algebra. Now take the square root of both sides and you get t equals the square root of 2d over g. All right, now, what kind of units would this have, you think? And we have to be careful here, and that's why some of you missed the extra credit question, because the distance, let's say you measure the distance in centimeters. If you measure the distance in centimeters, what's going to happen, because little g is 9.8 meters per second squared. So what's going to happen when you have centimeters and meters, it's not going to cancel out, right? I need those distance units to cancel out. So the first thing you want to do is you have to change all the centimeters into meters. So for example, 5 centimeters would equal 0.05 meters. So let's say you're going to make a stick, and somewhere on that stick, now no one's going to catch it within 5 centimeters, first of all. It's not going to happen. But if someone were to catch it within 5 centimeters, how would you find their reaction time? I would change 5 centimeters into meters, and I plug it into the equation. So here's what you do with your calculator. 2 times 0.05 divided by 9.8. And then what do? 2 times 0.05 divided by 9.8. Now I have this number sitting in front of me. What do I do with it? square root it. All right, I like it. I said 3. I like to have 3 sig figs. You don't mind? And I've had people do 4, but it just takes more space. But anyway, for example, here's one that was done, and you can see what's going to happen here. The meters are going to cancel out, and that leaves you with seconds squared, and the square root of seconds squared is seconds. So what we're going to do is turn a stick into a timing device. Now, so what are the rules on the stick? So here's what the first thing you might want to do while you're watching TV or something like that. You could actually, on a piece of paper, write 0.01 meters, 0.02, 1 centimeter, 2 centimeters, like that. You can do that. You can make a chart, and you'll have to do it about 50 times. So I think that, what's it say the minimum is on the, let's say something about the minimum on the stick. How many? 80. Is it 80? All right, you're going to do 80 calculations. Or, if someone in this room or someone in another room knows how to program your calculator, and I'll give you this, right? You can't steal their numbers, but if they'll teach you how to do that on a calculator, and you do it on your own, then you have all the numbers right in front of you. You get that? You can make a little tiny program on a calculator that you just put in the variables, say 1 through 80, and then you push a button, and it'll do all of it for you. Or you can sit there and do it 80 times. Yeah. Either way, you got to figure out what is 0.05 meters going to be. Now, let's take a look. It says here, to construct the stick, you need a sturdy material for repeated catches, because you might have lots and lots of catches. Get that? And so you have to be safe. That means no splinters, okay? You're not going to, don't have somebody do an experiment and your thing's got all kinds of splinters. Don't do that, okay? 2, the 0 should not be the end of the stick. For example, you can see the stick here. The 0 is not the end of the stick. There's a 0 right there. They understood that, because when you're doing this with somebody's hand, you really don't want the bottom of the stick to be. You want to actually already be in between their hands, and that's where your 0 point is. See that? So the 0 should not be the end of the stick. It should be up some distance. Next, a minimum of 80 centimeters should be labeled on your stick. Next, your stick must be color-coded for the times, and this is the biggest mistake people make. I'll show you one that was not a mistake. This one was a mistake. Okay, now, I love the colors, and they did a great job on that. Okay, so they actually got some bonus points for the neatness of it and all that. But they got points taken off because what I want is every 1/10 of a second should be one color. So everything from 0 up to 0.1 seconds should be one color. Well, if you look right here, they stopped at 0.09. This line right here was 0.101. Don't you think a 1/10 of a second would be just barely below that line? Don't lose you on this one. But I'm going to go all the way up to 0.1 seconds. You get it? And this is 0.101, which is very close to 0.1, isn't it? So their purple should have gone all the way up to here. And then everything that says 0.1 until it gets to 0.2, and again they made another mistake. See 0.202, where do you think 0.2 would be? Wouldn't it be right here? So if they had done it correctly, they would have had this much purple, this much pink, and then the green would have been all the way at 0.3. See that? So, and you know what you'd have gotten? And why do I have it color coded? Now, why aren't these the same? Why aren't they the same length? It's accelerated, isn't it? What's that mean, to accelerate? Every 1/10 of a second, what's happening? Isn't it going faster? What's that mean, go faster? You cover more distance in the same amount of time. And if you do this correctly, whatever that chunk of distance is, how big is this one going to be? 3 of them, 5 of them, 7 of them, 9. Ooh, that's pretty neat. So they got a couple extra points for the neatness and the color and the painting, but they got points taken off because their lines are in the wrong place. Now, so you have to decide, what what you're going to do is your paint. You're going to put a piece of tape here and paint that, let it dry, or I don't know how you're going to do it, but everybody does it differently, get it? All right, so then between 0 and, you can say 0.1. If you want to cross out and say 0.1, you want to do that? Is that easier for you to understand? It says me saying 0.099. I want you to say between 0 and 0.1. How about that? And then between 0.1 and 0.2. How about that? Does that make it easier? All right. Now, so let's take a look at some sticks here. This is called a club. I didn't ask people to go out and buy the biggest dowel rod you could find, but they said they liked it. All right. But they wanted the experiment to be like that. They want people to, catch it like that. That's what they do. Here's one. See, very artistic, but a little more difficult to read the numbers. See that? Did you even see the numbers? So I like the fact they said I'm not doing mine like everybody else. And they used some kind of a tape that was. Anyway, that's what they did. Here's a flat one. I kind of like this one. Very easy to read the numbers, and see that? And they went all the way up to 0.1. See, good job. Hayden Wilson, man, I haven't seen him for a long time. But this is his, and that's what his looks like. My own opinion is this is still hard to read, doesn't it? Just dark print on dark. So I know you have your favorite colors, but don't get too dark on it. How about that? Here's one, another round one here, and they did the handwriting, just took their time, and probably with a marker, something like that. Are you okay now? So it doesn't have to be round, it can be flat. Okay? Anyway, so that's the stick. Now, I think a lot of you could do a great job on that, as long as you don't wait too long. I've had people wait, and they have like 3 days ago, and they haven't made their stick yet. It's like, don't you have to let it dry and write the numbers on it and then do your experiment? That's waiting too long, don't you think? So maybe if you could get the stick done this weekend, you can say, oh, I still got almost 2 weeks. I got 12 days. I'm sure I can do an experiment in 12 days. Now, what I'm looking for in the experiment now is you get to design it. And it says here, create a self-designed experiment using your reactometer. And the due date is April 1st. Just happened to be April Fool's Day. Just happened to be. All right. Now, when you design an experiment or experiments, I've had people just get into this really well. You have to investigate some kind of independent variable that you think might have something to do with reaction time. So I don't know what you're going to choose for your independent variable, but everybody's dependent variable is going to be what? Everybody's dependent variable is going to be what? Reaction time. Got it? This problem will be stated, followed by a hypothesis. So you'll say, might say something like, what are the effects of a person being dizzy on reaction time? And your hypothesis would be, I think that when a person gets dizzy, their reaction time will increase or it will decrease. See something like that? And then you would have a data table, right? You have a data table. And what kind of data table you have? Well, it all depends. If you want to control all the other variables, you have to be careful about who you choose. Like if you said, I just want to see about dizziness versus reaction time. What happens if you take an 8-year-old and a 28-year-old? Well, now you're adding another variable, aren't you? So you might have to try to say, well, maybe I need to go find 20 people, at least 15. Let's say 10, absolute minimum 10. I need to have 10 people who have to do this when they're not dizzy. And then those same 10 people do it when they're dizzy. You get that? And you might want to say, I think I might as well take 5 males, 5 females. Or I might do maybe the same age group. You might decide to do 2 experiments that said, I'm going to do this age group, and I'll do another age group, the same thing, and we'll find out another experiment. It's like 2 experiments in one, isn't it? All right. Anyway, I want to it says be creative. Don't just say right-handed. I don't want anybody to turn it in and said, I want to see if your dominant hand, if you're going to do dominant hand and non-dominant hand, do something with it. I don't mind if you do dominant hand, but do something with it, okay? I had somebody one year, they had people catch it with their feet, okay? I thought that was kind of creative. I've never seen anybody do that. And so what I'm going to do is I'm going to talk about, for about 3-4 minutes here, let's talk about how are you going to do this experiment. So I'm going to get okay, so let's say so let's say this is my experiment, and I want to, why am I spending the time, why would I spend this much time making my stick, doing my experiment, so I can mess up the actual experiment? If you're going to take this much time to do it, then don't you want to do the experiment scientifically? So you can't mess around. You can't say, you can't do something like this. Hey, here, catch this stick, and okay. You can't do that. You have to have a way of doing it, procedure, right? Your procedure may be that they all sit down at this table. And you say their table, maybe their procedure is also, they must have their hand on the table so they can't go down and catch the stick. And please don't do this. This is going to ruin everything. Because if they get ready, you catch it now, you tell them, say, I don't want you to react until you see it fall. Just tell them, because otherwise they'll go, oh, you know, like a dollar bill. I want you trying to guess. I don't want them to guess. All I want you to do is you react when you see it fall. You get that? And just make that clear to them. And so you might do something like this. Hey, let's just practice a little bit and just I'll do it again. All I want to do is practice. Wow. And all we're going to do is say, you know what? I just want you to get used to catching it. Okay, now we're going to do 3 real ones. Why am I doing 3? I want to do it 3 times and find the average, don't I? You're going to write that in there if you don't think that's... And you can do it 5 times. If you don't do it 5 times to do the average, that's up to you. But you'll have to have a data table ready that says subject number 1. Trial 1, trial 2, trial 3, average. Okay? Now, we're going to do the real ones now, right? And again, she's not supposed to guess. She's not got my 0 right here. Okay? Now, right here, I take this, and I write that down. And you don't have to tell her. You don't have to tell her what it was. Ooh. Wow. Now, if I thought, okay, sometimes I have to be careful, because I think that time I did, it was wiggling a little bit, and I tried to steady it, and then she said, he's probably going to drop it after he said, I can just say I'm not going to count that one. Because I'm all right. She might have the. Oh! Okay, just remember, wait a minute. This is your experiment, and if you feel like something's not going right, you have to let them know. Say, look, I really want you to wait until you see the stick drop and then react to it, okay? And then I understand. So, can everybody get that? Otherwise, you're really wasting your time. All the time you spent making this, you're just wasting it. All right, now, so you're going to try to have 3 trials, which you might call your control, your normal. But then you have this variable, and I don't know what your variable is. I've had people say they had to listen to this kind of music, or they had to listen to this kind of music. I've done that. I've seen people do that. I've seen people. I've done the Disney. I've seen the Disney thing before. I've seen combat where they had to go and run as fast as they could. They ran around something. They ran around a building or something like that, and they came back and did it again. And that was just their experiment. They thought, you know, I think if you're running, you're kind of breathing hard. They thought the reaction time might be faster. Okay. Now, we can't tell anything with one person. So I would say it has to be at least 10. 20 is better. And if you want to do 30, you can do 30. But I'm just saying, if you do something less than 10 people, and maybe you have 5 males, 5 females, I'm not sure it's a very good experiment. So I'm going to say if you had less than 10, it's going to be bad. But I would expect more than 10. How about that? So if you can get more than 10, that's great. I think 20 is a great number. I like 20. Miss Church, if you were taking stats class, she allows this experiment to be expanded, and they have a minimum of 30 people, and they have to do all the statistics on it and that kind of stuff there. So you can ask her if she's still willing. We couldn't do it last year because of COVID, but you can ask her if you can still do that. And she'll put some other restrictions on it, and it'll be a bigger experiment, but you could actually do 2 for 1 that way. All right, so what do you think? I know you have to think about how to make the stick, but that's one kind of problem solving. But the other one is, can I come up with a creative experiment that I really do want to know what happens to reaction time? I don't want to give away, I don't want to tell you what to do. I'll just tell you some that I've heard in the past and say, well, if you did it that way, I'll do it this way. Like, I had a person who actually made a device, and it had a magnet here, and he pushed a button. Instead of him releasing it with his fingers, he pushed a button and it automatically fell, because he thought it had something to do with the person dropping it with their fingers. Another one you have to be careful about is, could you have the person, their eyes are closed, and they have to wait till I say, stop! They have to react not with their eyes, but with their ears. That's kind of interesting. But just be careful. If you feel like something's not right, it's your experiment. You can tell the person, say, look, I really want you to wait until you actually see it drop, and then react, okay? And then I think if you get an average of 3, it should be a pretty good number, all right? Now, what kind of graphs would you put? Well, if you were doing the same person, and you said, I'm doing the same person, I'm gonna do it at 8 a.m., 10 a.m., and 2 p.m., and 2 a.m. If I had the same person, and I did it on the same day, then maybe I would have a line graph. But because it's gonna be different people, you're gonna have to use bar graphs, aren't you? So you might have a bar graph, say, here's a bar graph normal for this person, and with my experiment. See? Their normal was like 0.252, and after they got dizzy, it was 0.303. And so you have those 2 bar graphs, but for whatever reason, I'm not sure, every year, what's the one bar that's left out? They have these 10, 15 people, normal, experiment, and I got all 15 people with bar graphs. What's the one I really want to see? The average. I'm not sure why you wouldn't give me the average. So if you want to say if it's male versus female, I should see the average for the males and the average of female on a bar graph, shouldn't I? Don't make me get my calculator out and do all your data for you. Get that? And then also, after you get your data table and your graph, what kind of graph, you have to make a conclusion. And the conclusion is based on your hypothesis, or your hypothesis, right? Well, I thought that this was happening, but I found out that really there was no effect. There was no effect of that. The difference is only 1,000th of a second, and I hereby declare that the stats, they have to use t-test. What do you guys call them, t-test? What do you call it when you figure out whether something is actually not random? Is that called p-test? T-test?
The value is a p.
Is it t-test?
It's a p-value.
P-value, but it's a t-test, isn't it? Is it called t-test?
We call it like 1 proportion zeta.
Okay, hey, but you guys, because you guys aren't in stats, I wouldn't expect you to do that. Get that? Now, you might just say something like, well, I found it was a 10% drop. You could at least do some ratio things, like it was a 10% less. The reaction time, and by the way, you know, if the reaction time is less, that means they're faster. You understand that? If the reaction time is greater, that means they were slower. All right, what do you think about this project?
I think it's cool.
I think if you allow it, if you spend just a little bit of time, and I know you have to make this stick, but I love the fact that you're gonna create, I should not have identical experiments. I just can't believe that you can't come up with your own experiment. Get that?
Do we get partners?
I'm not going to, but I did in the stats class, some of them were doing experiments that were so involved. They were doing like 50, 60 people. I did have, if Miss Church told me that they were doing it in partners, that's the only time I've done partners, but normally I don't. And they'll turn in a paper that's like, 8 pages long. You guys will not. So that's why it almost took 2 people to do that for them. But right now, I'm not doing that 2 people, so. All right, what do you think? What do you think? All right, so April 1st, that's 2 weeks from Thursday, I think it is, right? So you can at least tonight say, I'll think about this. Do I have a piece of wood at home, or do I have what do I have that I could mark? And you're going to be marking these every centimeter, aren't you? Is that right? So you know it's going to be marked every centimeter, and then eventually you're going to paint it. So do you want to paint it and mark it? Right? Does that work better? I don't know how this person was able to get such straight lines. What do you think? Well, however they did it, and then see the little typing thing? That's the way they decided to make theirs, and then they taped it on there.
And not paint the back.
I don't think you have to. I do. Oh, by the way, well, this person, they graduated that's almost 12 years ago. But she was a hockey player. Girl, she actually went to Raleigh and played. She got to go all over the place to play hockey for hockey player. But I think she ended up going to University of either Penn State or Pittsburgh. One of those. She went to one of those universities over there and played hockey. She was also very smart. Anyway, I do have to have some way to put your name. Put a little note on there. Please put your name on it. There's no way, if I get 20 of these sticks and they don't have names on, there's no way I can tell. So some people put back here on the back. Some people, they had the club. Let's see, that was a bad one. No name. Okay, please make sure you can put your name on there somewhere like that. All right, what do you think? I'm done talking about that. All right, now, if you come up with some kind of question, and in tomorrow's class at the beginning, when I'm getting ready to start to teach, just say, can I ask you about that project before we get started? And I'll say, yeah, what do you want to know? All right. What I'd like to do now is the next thing we're going to be doing is actually chapters 5 and 6 together. Now, you might think well, that's a lot, but it's not, because I can tell you right now, we've actually already done quite a bit of chapter 5, and we've actually done a certain amount of chapter 6. You don't know that, but the ideas that you already have are found in 5 and 6. So what I'd like to do is, if you have your book with you, I'd like you to turn to chapter 5. I'm sorry, chapter, did I say 5?
Yeah.
6, okay. Okay, I mean, we're doing 5 and 6, but I'm doing 6 first. That sounds weird, doesn't it? I'm doing 6 first, and then we'll go back to 5, okay? All right. So let's take a look, and believe it or not, we've already done some of this. We've actually already done this. And this chapter is, what is Newton's first law? What was Newton's first law of motion? Anybody know? It was mainly developed by Galileo. And yet, Newton didn't sit there and said, these are my 3 laws. He didn't. Newton said, I think I can explain the motion of almost anything in the universe in 5,000 laws. No. 1,000 laws. No. 10 laws. No. 3. He said, I really only need 3. That's what's amazing to me. That most of the motion of anything in the universe can be explained in 3 laws of motion. I find that unbelievable. You mean when a leaf drops and goes like this, that can be explained in 3? Yeah. You mean when a planet goes around the sun? Yeah. And so that's amazing to me, to think that it only takes 3 laws of motion to figure out why things move. Now, the first law of motion, you actually already know, it's called the law of inertia. An object at rest tends to stay at rest. An object in motion tends to stay in motion in a straight line at a constant speed. Again, unless acted on by some kind of outside force or something like that. All right. So we've already done that one. So let's take a look at this chapter here, chapter 6. Now, do you remember that in the last chapter, if I said find the acceleration of something, the definition was the change in velocity over time, isn't it? Isn't that right? And so if you went from 10 to 30 miles per hour, and it took you 2 seconds, what would the acceleration be? So if you went from 10 miles per hour and you went to 30 miles per hour, and that took you 2 seconds, what would your acceleration be? Let's see if you can do that for me. You went from 10 to 30 in 2 seconds. What's your acceleration? Now, raise your hand when you think you have a good answer. All right, we got.
10 miles per hour per second.
Okay, what do you think? Okay, let's take a look. What was delta V? Delta V was the second velocity minus the first. 30 minus 10 was 20 miles per hour. And then I divided by what? 2 seconds. And so my acceleration is, what did you say the answer was? 10 miles per hour per second. Excellent. That's excellent. 10 miles per hour per second. Also written as 10 miles per hour second. Everybody got that? So we already knew that from last chapter, didn't we? But what you're going to see here is kinematics is the mathematics of motion, isn't it? But what Newton was good at was what they call mechanics. Mechanics is not just the kinematics, but why? What's the cause of it? What was the cause of that acceleration? And now you're going to see another equation. What's the second equation for acceleration? Well, first of all, I want to tell you that Newton's second law, if you just look at it in book, it's going to look like this. It's going to say F equals ma. Now, there are people that think that's one of the most amazing, astounding things that any human has ever come up with. It doesn't look that way, but the fact that he related force to mass and acceleration, and he said he knew who was directly proportional and who was inversely, they think that's amazing. Now, let's try this. Rearrange this until it solves for A. A equals what? Now we have two equations for acceleration. Now, why would I need two? Well, the first one was used when I gave you the initial velocity and the final velocity and the time. If I give you that information, I have to use that equation. But when would I use this equation? Well, what if I give you the force on an object and its mass? What if I say a 10 Newton force is applied to a 10 kilogram object? How much acceleration would I expect? And you can calculate that. You see that? So it all depends on what kind of information you give me as to which equation I use. All right. Let's see how much you know about F equals ma before I start teaching the chapter. All right. Ben, you're going to do it, okay? F equals ma, right? Tell me about how F and M are related to each other mathematically.
Directly proportional.
When?
And A is constant.
Yes. Yes. All right. Now, let's pick another person. Parker. He did F and M. You do M and A.
They are not directly.
What now?
Nothing. They are. It is inverse proportion.
What?
Inverse.
Do we have a whole chapter on this? Do we have a whole unit on
I
this?
don't think so.
What was it? Okay, first of all, I'll give you a clue. They're on the same side of the equal sign, and nobody's being squared or square rooted. So what are these? They're inversely proportional to each other if what? If what?
The force is constant.
Right.
Yes.
All right, one more time. One more. Lily, tell me about F and A.
They are directly proportional and then
Okay, now, so far, everybody should be able to do that without me helping you. Now, the next thing you want to be able to do is, can you, this is higher level, can you apply that to a situation? Let's do the first one, F and M. I happen to know that in a vacuum, all objects have the same acceleration. Get that? That means acceleration is going to be constant. And so if I drop a feather and a bowling ball, if I drop a feather, then the force on the feather is like tiny, like 1/100th of a Newton. And the mass is really tiny also, like 1,000th of a kilogram, something like that. But what if the bowling ball has a mass that's 10,000 times greater? If the bowling ball's mass is 10,000 times greater, then what's the force on that bowling ball compared to the force on the feather? Now, we had a whole unit on this. Try it again. They're directly proportional. So if mass got 10,000 times greater, what's the force on that object? And it has to be 10,000 times greater than it was on the feather.
Yeah.
Now, if you flip this paper that I gave you over, they don't have this cartoon anymore in the new edition, so I don't think it does. So I pulled it out of the other edition of Paul Hewitt's book. And let's talk about this. Why, in a vacuum, do two objects hit the ground at the same time? And I promise you, it's not because they're pulled the same. They're not. Earth's gravitational constant is not the pull of anything. It's the acceleration that gravity gives to you. But Newton says the acceleration is due not to the force on you, but the force per mass. And every object in a vacuum, everyone, has the same force to mass ratio. That's why they all have the same acceleration. Now let's take a look at this. He made a little cartoon about this, okay? Here's this lady with the curly hair says, if I drop this bag of clothespins and the single pin at the same time, which one will hit the ground first? That's easy. The bag of clothespins is heavier. True or false?
False.
Okay, wait. What I need you to do, wait, listen. This is important. As I stop, I want you to think and then say the answer. Let's try it again. That's easy. The bag of clothespins is heavier. True or false? It is true. Which means that gravity pulls on it with more force. True or false?
That's true.
That's true.
That's true.
False.
So the bag of pins will accelerate more.
False.
That's
False.
false.
You do it.
And hit the ground first.
False.
That's false.
True.
All right, next. Ready? Not true. Not true. The bag of clothespins has more mass.
True.
True. Which is to say, it has more inertia.
That is true.
I'm looking at you. That's true. It will be less responsive to gravity and lag behind the single pin. So the single pin will hit the ground first. What do you think?
False.
Hey, stop, please. Stop.
I'll say.
What do you think? True or false?
False.
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 Now, I don't know if you noticed this or not, but way over here, this is the nosy neighbor.
You do it.
And
I like that.
see, the nosy neighbor, she's been listening to the conversation the whole time. And it says, sorry, gang, a tie score. How come? See, he thought the bag would hit first. He thought the single pin would hit first. And here's the nosy neighbor who I guess really does know how. It says, since the bag has both a greater weight and a greater inertia, that's mass, is that true or not? If it has a greater weight, that's force, and a greater inertia, that's mass, and a greater inertia, it offsets each other, meaning you could have a greater weight and a greater mass, or a smaller weight and a smaller mass, and still have the same acceleration.
So you hit the same time?
And they would hit the same time. What do you think? Okay, now, hang on. What I'm trying to do today, I'm trying to lay the groundwork for this chapter, and I think some of you did well last chapter, except some of you thought, like when I told you that acceleration is not as easy as you thought it was. Acceleration is hard to conceptualize sometimes. And I think some of you thought it was, and I think that's where you missed most of your questions on when it had to do with acceleration. All right, let's take a look again. F equals ma is Newton's second law. But I want to tell you about some details. Let's talk about some details of F equals ma. Number one, it's not force. It's actually net force. Now, we talked about that the other day. You have many forces acting on something, but what if all the forces add up to zero? Then what's the object doing? What if the forces on object, many forces add up to zero? What's the object doing? Now, I want you to be serious here, because I need to know if you even forget some of the stuff from the other chapter. If a net force is zero, that means it's at equilibrium. What's the object doing? Anybody?
Staying constant.
What now?
Staying constant.
What's that mean?
Not.
So is it sitting still? It could be sitting still.
Oh,
That's true. That's one
True.
of the conditions. But there's another way that the net force could be zero.
Constant speed.
What?
Constant speed.
In a straight line.
it's
You could be going in a straight line at a constant speed and still have an equilibrium of
zero.
zero.
Ooh.
Yes?
Awesome.
Okay, now, what I'm going to show you then is, when they say F equals ma, what they mean is net force. Now, I got to tell you how this looks so simple. This equation looks so simple, but I'm trying to show you why it's so ingenious. Okay, watch now. If we have a mass and it's not zero, so let's pick any number you want for a mass. That's a real number, isn't it?
2.
Okay, whatever the number is.
It's 2.
Wait, I'm gonna listen. If there's a net force, if there is a net force, there's just some number, it equals some number times what? If there's a net force, acceleration cannot be zero. Cannot. If there's a net force, I'm sorry, my fault. I did it wrong. If there is a real net force, then there has to be acceleration. It can't be zero, right? So if there's a net force on you, you must be accelerating. You must be. Anything that has a net force on it is not going to be moving at a constant speed. It is not going to be sitting still. It's going to be accelerating. It's either going to be speeding up or slowing down. That's detail number one. Detail number two. This is a vector quantity. And since this is a change in velocity, which is a vector over time, this is also a vector. You need to know, if the net force is in that direction, the acceleration will be in that direction. It does not tell you what direction the object's going in. It tells you the direction of acceleration. So, when an object is in a car and I put my foot on the gas pedal, if I cause a net force in that direction, then I will accelerate in that direction. And I'll actually see the speedometer needle go up and up and up, won't I? But if I take my foot off the gas pedal, okay, then what's going to happen? I'll see the speedometer needle go down. Now, what direction is the acceleration in? I'm going that way, but I see my speedometer needle going down. So why would I be slowing down? I'm going that way. Why am I slowing down? There must be a net force in what direction? Backwards. But I'm going this way. That's okay. The net force is in that direction. The acceleration is in that direction. And if the acceleration is in the opposite direction you're moving, you will slow down. I keep looking at your faces because I don't want to lose you on this. This is kind of the neat part of this thing. There's no way mathematically, if you are accelerating, you must have a net force on you. If you have a net force on you, you must be accelerating. Now you're going to find out later. You're going to find out later that there are objects. Let's see if I have one here. The feather in the vacuum is one thing, but the feather not in the vacuum is another. So as soon as I go that feather, you would think the Earth is going to accelerate it, don't you?
Yes.
Okay. Now what's interesting about these two objects, let's do another object. Let's do this object, see?
I couldn't see it. Well,
So in this chapter, we are going to talk about air resistance, and we're going to say, why is it in the air, why does this object always beat this one? And we're going to talk about that too, okay? So that's going to be coming up. So right now, we know there are two equations for acceleration. One of them we learned last chapter, and then this is the one here. If we rearrange that and form like that, and now we know what those mean. Now, here's something interesting. Now, author is an artist, and he drew everything in here. He drew it. Matter of fact, you can go online, and if you wanted, there are some teachers that get into this so much they go into there's a bank, a drawing bank, and it's called Hewitt Druitt. Hewitt Druitt. His name's Hewitt Druitt, and you can actually click on there and put that on your test, and he has all kinds of things like this. But does anybody know why this has anything to do with this chapter?
because the force to push it forward is well.
What now?
Because the accelerator produced depends on the mass that it push.
What's that mean?
That like it takes a lot more acceleration to push on a mass.
A lot more what now?
Acceleration, force,
The same thing?
yes.
No.
No. I know.
False.
Force is the F, acceleration is A.
Okay, what do you think? All right, so wait a minute. Parker, wait, listen. Wait a minute. Wait, please. Shh. Wait. Listen, I thought you started out really well.
Oh, I started out.
Okay, now, so let's take one of these shopping carts. You guys like calling them buggies, that's right. So you want to take a shopping cart,
I like
and what if I want to accelerate? Wait a minute. Everybody stop. Okay, so if I have a shopping cart that's empty, and I want to accelerate it, it's going to take a certain amount of force, isn't it? But if I put a hippopotamus in it, and I want to accelerate the cart the same amount, what's that mean? If I want acceleration to be the same, that means it's held constant. But now I have a shopping cart whose mass is like 100,000 times greater. Then what do I have to do? I have to come up with 100,000 times more force because they are directly proportional. And that's what they're trying to show here. Get that? All right, show the page. Oops. All right, so we talked about this. This is last chapter. And this is this chapter. And this is the last chapter here. Now we go over here, and we're going to do a problem. So let's do some mathematics. Now, what I'd like you to do is, if you have a piece of paper somewhere or you have a calculator, let's try to do a simple math problem here, okay? All right, ready? All right, right here. It says here a car has a mass of 1,000 kilograms. What is the acceleration produced by a force of 2,000 newtons? Now, is it obvious to you that you cannot use the equation from last chapter because I don't have the final speed, I don't have the initial velocity, do I? I have to use the one for this chapter. So we're going to use the equation F equals ma. Now, what are they asking you to find? What is the what? So I'm going to take F equals ma, I'm going to rearrange it. And what's it going to look like? A equals F over m. Now go find the force. Which one's the force up here? Which number is the force?
2,000 newtons.
Newtons are force, aren't they? So I'm going to plug that in for the force. And what's my mass?
1,000 kilograms.
And this has to be in kilograms. Okay, now, watch what happens here. 2,000 divided by 1,000 is 2. So I know how the number I got, but look at the units. Look at the units. A newton, and I need you to memorize this, a newton is, by definition, a kilogram meter per second squared. It's a kilogram meter per second squared. I'm going to show you, thank you. I'd like to show you how to memorize that. How can you memorize that a Newton is a kilogram meter per second squared? Yeah. Okay, now, I'm going to wait till everybody's looking up here. Everybody look up here. How can I memorize that a Newton is that? Well, what is Newton's second law? See the F equals ma?
Yeah.
What is the SI unit for mass? Kilograms. And what is it for acceleration? Meters per second squared, isn't it?
Yep.
So what is a kilogram times a meter per second squared? It's a kilogram meter per second squared, and that's supposed to be force. And force is measured in newtons. So if you ever forget that, just equals F equals ma, kilogram meters per second squared, newtons. Get that? Let's go back to our problem. I'm going to replace the word Newton. Let's replace the word Newton with kilogram meters per second squared. And then I'm going to divide it by kilograms. So what happens here? What happens here? What's kilogram meters per second squared divided by kilograms? And I'll give you a hint. I'll give you a hint. It better be units that sound like acceleration. And it is. Meters per second squared. Got it? Okay, do the next one. If the force is 4,000 newtons, what's the acceleration? Okay, now what we could do is we could do it just like that one. We could plug it in here. It's called plug and chug. We could plug these numbers in and get this answer here, or we could have done it this way. If this was 2,000 newtons and this is 4,000 newtons, what happens to acceleration if force is doubled? If force went from 2,000 to 4,000, it was doubled. What happens to acceleration?
Has to be doubled.
It'll be doubled,
Exactly
and so
proportionate.
that's right.
As long as the mass is 7,000.
Everybody see that? Now let's stop for a minute. Because it's the first day of the chapter, it's very important that you soak this in, because tomorrow you want to review it a little bit and say, I think I got this. I think I got this now. Let's do one more. We have time for one more question. Try not to look at the answer. Don't look at the answer, okay? Try this one right here, and without looking at the answer, see if you can come up with this one. How much force or thrust does a 30,000 kilogram jet plane develop to achieve an acceleration of 1.5 meters per second squared? Now, without looking, see if you can come up with the answer.
What's the mass again?
It's a 30,000 kilogram jet plane, and we want to have an acceleration of 1.5 meters per second squared.
So
That's
Now,
gonna be
do the
acceleration.
work and see if the units come out right. See if the units come out right. Bennett, do you really have the answer?
No.
Okay.
Calculating.
So you said it
I was
was
trying to do it in my head,
23,000?
but I can't.
3,500?
I can processing data.
Hold on. Shh. What you got?
So 45,000 newtons.
Okay.
45,000 newtons.
All right, hang on. Shh. Watch now. If we go down here, and they gave me the mass, and then they gave me the acceleration, so we end up multiplying. And look what happens here. We get kilogram meters per second squared. But what is a kilogram meters per second squared? It's a Newton. And that's good because I need force, don't I? All right, now that was a lot for today. And